Sun's rotation is slowing down, and this is why they are struggling. The Sun's rotation has slowed over time, which explains the composition of its surface. A mysterious discrepancy between Sun models and measurements of its composition has been resolved, by taking into account how the star's rotation has slowed over time. Dr. Patrick Eggenberger of the University of Geneva, UNIGE, and his colleagues conducted the research. Because the Sun is the star we can best characterize, it serves as a fundamental test for our understanding of stellar physics, Dr. Eggenberger said. We have abundance measurements of its chemical elements, but also measurements of its internal structure, as with Earth, thanks to seismology. Ideally, all of these real-world measurements would correspond to the Sun's properties as predicted by the models developed by physicists to explain the star's evolution. These models aid scientists in their research into topics ranging from how the Sun burns hydrogen in its core to how chemical elements move around the star. The standard solar model performed admirably until the early 2000s, when an international team published revised measurements of chemical abundances on the Sun's surface that contradicted those predicted by the model. Since then, the proposed new abundance values have withstood multiple verifications, implying that the issue must be with the solar model itself. The standard solar model we used until now considers our star in a very simplified manner, said paper co-author and astronomer Gal Buljan, also of UNIGE. She explained that this oversimplification applies not only to how chemical elements are transported within the Sun's deepest layers, but also to how the Sun rotates and the nature of the internal magnetic fields it generates. Over the last 2 decades, various new models have been proposed to explain the new chemical abundance measurements. Until now, however, no one had been able to adequately reproduce the data obtained from helioseismology, the study of the Sun's oscillations, specifically as related to the abundance of helium in the Sun's convective outer layers. Dr. Eggenberger and his colleagues' new model reconciled these differences by taking into account both the evolution of the Sun's rotation, which they believe was likely faster in the past, and the magnetic instabilities that this causes. The team assumed in their model that the Sun was initially rotating around 5 times faster than its current equatorial rotation rate. We must absolutely consider the effects of rotation and magnetic fields on the transport of chemical elements in our stellar models, Dr. Eggenberger said. It is as important for the Sun as it is for stellar physics in general, and it has a direct impact on the chemical evolution of the universe, given that the chemical elements necessary for life on Earth are cooked in the cores of stars. According to the researchers, their new model accurately predicts not only helium concentrations in the solar envelope, but also lithium concentrations, another element whose measured abundances on the Sun's surface had previously proven difficult to match in models. The abundance of helium is correctly reproduced by the new model because the internal rotation of the Sun imposed by the magnetic fields generates turbulent mixing, Dr. Eggenberger explained. This prevents this element from falling too quickly towards the center of the star, he added. At the same time, the abundance of lithium observed on the solar surface is replicated because the same mixing transports it to the hot regions where it is destroyed. However, the new model does not address all of the issues. Thanks to helioseismology, we know within 500 kilometers, 311 miles, in which region the convective movements of matter begin, 199,500 kilometers, 123,964 miles, below the surface of the Sun, explained paper author and UNIGE astronomer Dr. Sébastien Salmon. However, theoretical Sun models predict a depth offset of 10,000 kilometers, 6,214 miles. The new model has shed light on the physical processes that can assist us in resolving this critical difference. Thank you very much for watching, my dear. Please subscribe by clicking the button below.